as promised. So we're switching gears to tackle the other half of the preliminary material that we need. Hello again. Please come in. No worries, no worries. I thought we'd have more coming, and I'm just glad folks came back. So we'll take that as the compliment that it is. So multi-level measurement models, right? That's the title of our workshop. And so far we've had measurement models. And in learning all of those topics and their complexity and estimation, we completely ignored the fact that these 3,100 cases are children who are nested in schools. And to the extent that some schools have more resources or better teachers or what have you, we would expect some commonality in the performance on these math questions and some commonality in the latent trait that underlies their answers to these math questions. Yes?
I think I found my problem.
Oh, okay, stop the presses.
Sorry.
An important update.
Model fit didn't work well in my live example. When I changed my code, I forgot to select just a person's data, and it was doing all sorts of craziness with all the thetas in the loop. So now I will rerun and fix, and I'll fix your handout as well too. So pardon me.
Okay, stay tuned for the next exciting
Sorry
installment.
to interrupt. It's like really got me sideways. I'm just traumatized by this. Sorry to interrupt you.
No worries.
Professor
All
Hoffman.
3,100 thetas, as you were saying, right?
Good. That's why the numbers were so discrepant.
Okay, that makes complete sense to me. So we ignore the fact that there's clustering, as we would say, that there is some correlation of students who attend the same school in the same educational context. And what I'm about to do is ignore the fact that there's measurement error. So I'm going to be working with, in the example that follows this slide deck, a sum score of the 10 items, which is less than ideal, but it's a necessary compromise to be able to present the fundamentals of the multi-level side. Then the exciting conclusion is to put them together probably tomorrow afternoonish. We're not sure. We'll see how long it takes to get through there, but hopefully tomorrow, and if not tomorrow, on Friday for the exciting conclusion.
The preliminaries will be tomorrow.
Yes, the preliminaries will be. So I decided, for two reasons, to focus on the case of clustered data. So people who are part of naturally occurring groups, like siblings within families and students within classrooms and that sort of thing, for two reasons. One is that it goes along with the example. So we have this working example that goes throughout the workshop of student math items within students who are nested in schools. And second is just because I already did longitudinal last year, so I wanted to give you some variety. But then when you all introduced yourselves and several of you said, I have longitudinal data, I went, uh-oh. So if you're listening to this and thinking, does this apply to me, or how does this apply to me in the longitudinal case, I am very happy to step out of this clustered context and address how it would differ or whether it would differ in a longitudinal context. I also want to say that even though I'm saying this is a transition to multi-level models, would you believe me that we've been doing multi-level models all along? If you think of item responses as nested in persons, IRT is a multi-level model. CFA is a multi-level model. There's an expression, at least in where I'm familiar with, that if you have a hammer, everything is a nail. Everything is a nail, okay, folks? Everything is some kind of multi-level model. So understanding sort of the basics of how to do multi-level modeling, it transcends not just into one specific sampling design, but into a lot of different contexts simultaneously. So that's the background that I'm coming from. So what do they do? In this sampling context, we're talking about clustered data, otherwise known as nested data or group data or hierarchical data. And the key idea here is that these outcomes come from a sampling design where there's more than one type of sampling happening simultaneously. So in this case, we have students as one level of sampling, which we would call the micro units, and they occur in schools, which are the macro level. In longitudinal data, we have occasions as the micro level, within persons usually as the macro level. I just finished teaching a full year-long sequence of longitudinal models, and I had a student who was studying businesses and how they change over time. So that was occasions within organizations. So all different kinds of sampling, all different kinds of data that these are applicable for. And the key idea of multi-level is that the term level applies to each dimension of sampling. There's differences between schools, there's differences within schools, there's differences between people and within people. And if we allow some kind of leftover variability that says, well, I don't know why people differ from each other, but I know that they do, I don't know why schools differ from each other, but I know that they do. That's what constitutes a level. And we can have just strictly nested levels, or we can have crossed levels. So I know some of you do experimental research where you might have people respond to the same vignettes or the same items. Technically, those are crossed dimensions, where each individual response is nested within a person and nested within the stimulus that the person is responding to. Technically speaking, any kind of item level measurement model could also be crossed if you don't allow for differences in the item parameters. So if you said that items differ randomly in their difficulty, for instance, rather than allowing a separate intercept per item. So those would be cross dimensions instead. And this is the term that I prefer for these type of models, is multi-level, but I have a whole list of synonyms. Yes, please.
I'm so sorry. Could you explain one more time a bit slower what is crossed?
What is crossed? Okay. So strictly nested means that there's that like each student goes to one school and one school only, right? So the way that I think about what is crossed is if you say to yourself, which way does my nesting go? And you can make an argument as to either making sense, it's not nested, it's crossed. So if you think about items and people, well, everybody responds, like each item is, everyone responds to all the items. So items are nested in people, right? And then some other person goes, no. Each item has responses from all the people. So people are nested in items. And both of those make sense. What that means to me is that they're crossed. So if I think about the response of a particular person to a particular item, it depends on who the person is, it depends on which item it was, and then there's some kind of leftover variability as to, well, I don't know why this person answered this way for this item. So then you have differences between people explainable by person-level characteristics, differences between items explainable by item characteristics. And so if you say an item characteristic is that it's item 1, and this is item 2, and this is item 3, and you allow a different difficulty and potentially discrimination for each item, then you've saturated all the reasons why items differ from each other, and that dimension goes away, and all you're left with is responses nested in persons. Okay, does that help? Oh, 2 thumbs up. Excellent. Other questions? I love questions. I especially love what some people might call stupid questions, because that means I might be able to answer them. No? Okay, please make sure you're not shy. So synonym time. And I say this because in different fields, these same models are called different things, and I want to make sure that you're aware of the parallels. So we have a colleague at Iowa who would talk about this exact same set of models and sampling designs as linear mixed effects models, where mixed effects means both fixed and random effects, where a fixed effect is a constant and a random effect is a variable. You might know them as random coefficients models, and particularly within education, the term HLM, or hierarchical linear model, is what tends to be used. There's a dedicated software package called that as well. I will note that it is not the same thing as hierarchical regression, which is a stepwise procedure of entering variables as predictors. So a lot of work has gone into describing the parallels between the world of multi-level and mixed effects models and the world of structural equation models. And where I think the advantages and disadvantages columns get a little bit mixed up is recognizing that multi-level modeling, by definition, in the way that most software implementation works, it's a univariate model. So the type of data that go into it is what's known as long format, where it's 1 row per response per sampling unit. So if I'm thinking about math, right, that's one idea, that's one column of data, and I'm going to predict it. So that's what those models are designed for, even though it might be longitudinal or clustered in terms of how the rows are organized across sampling units. It's still univariate. And what if you want to predict math and science at the same time? Could you do that? Sure you could, but you couldn't do it in traditional multi-level modeling software. You need something that is capable of doing a multivariate analysis. And so that's where the world of multi-level structural equation modeling comes in, what I still just call multi-level multivariate unless there's a measurement model involved. So multivariate extensions can be estimated using regular structural equation modeling software or multi-level variants of that. And the key idea is that you'd be predicting 2 columns of data instead of just 1. It's also a better way of addressing missing predictor variables. So today is the univariate case until the very end of the examples, in which I have one multivariate example. And what Jonathan and I are going to do for the examples tomorrow is show you what it would look like in LME4. Woo, says no one. And then show you what that exact same model would look like in STAN. Yeah. Although in contrast to what he was having to do, these things took maybe like a minute to run in STAN, and they didn't generate 1 million files and data points. So
You have one outcome that's hard to do.
I know.
For this predictive model.
It's like the easy STAN. So plus he has developed ways of coding that make people like me who had never seen STAN before able to use it to some extent. So I am happy to take advantage of his trickery and trial and error that he's come up with. Yes.
Maybe a stupid one.
Oh, good.
Yeah.
Excellent.
What do you exactly mean by addressing missing predictors? Or should I take that question to a later point when we discuss more about multivariate?
So I can say it now, just briefly. If you run let's go back to regular level regression models, like the first stats class that you had probably as an undergraduate or graduate degree. What happens to cases that are missing predictor variables in your regression model? Bye. Thanks for playing. They don't get included, right? We call that listwise deletion. The exact same thing happens in multi-level models as well. The rule is each row has to be complete with respect to all of the outcomes and predictors in the model for it to be included. So when people say, wait, I thought that multi-level models handle missing data. No, they don't. They don't at all. The difference is in the data structure. So that comment usually comes up in the context of longitudinal data, where people are contrasting a row that's a person and all their observations in a row. It is true that in routines that use ordinarily squares, like classical repeated measures analysis of variance, that if you're missing one outcome, you're gone, because then the row is incomplete. In multi-level models, a row is only one occasion, so each person's data is transposed across multiple rows. So incomplete occasions still get kicked out if they're missing predictors or outcomes, but whole people don't necessarily get kicked out. But what if you have a person characteristic, say in a longitudinal study, where you measure something at baseline and you don't measure it again, right? That happens fairly frequently with background information that's not expected to change. Well, think about the data set where it's 1 row per occasion per person. If they don't have that baseline observation, it's missing for all their rows. Bye-bye. Then that person is listwise deleted. So if you have multivariate software, if you have the capability of predicting multiple columns at the same time, you can trick it. And you can say, hey, what if I pretend that this column that I'm calling a predictor is actually an outcome? And you can basically estimate an empty model for it. You ask the software to come up with its mean and its variance. Then it's an outcome from the perspective of the likelihood function that's being built, and you can have incomplete observations. So multivariate is the key to not having listwise deletion happen for your predictors, particularly at the person level. Jonathan, anything you want to add about that? No. Okay. Well, and this is frequentist land, by the way. I'm not in Bayesian land right now.
One small thing.
Okay.
She mentioned the type of data being long format.
Yeah.
When you get to STAN, you can throw out all the formats because you control how the data go in and how they're analyzed. So if you want it wide, you can make it wide. If you want it long, you can make it long. And the final example, we have some wide and some long. So leave space in your brain for having different data. And this is actually a piece where she and I speak very different languages.
Yeah.
Because she'll be like, well, the data have to be long or they have to be wide. I'm like, no, they don't. They can be whatever you want them to be. The model is the model. You just give it the data. And so just leave a little space in your brain to not have a shape of data discussion. That's all.
That's because I'm used to using software that forces you into one mentality or the other. And so you can estimate the exact same model, for instance, using long data or wide data, but the code looks different. And so you have to know that to be able to describe how you want your model to be organized. All right, slide 2. I know, I'm great pace. Anything else right now? Okay. All right, more words to ask the Google about when you're trying to make connections across models. So when you are dealing with only one dimension of sampling at a time, so let's say it's a cross-sectional study of people, and the people are not organized into families or classrooms or schools or anything, then the world of general or generalized models would be applicable, where general means a conditionally normal outcome. Generalized means any other kind of outcome. So ized models are things like logistic regression for binary outcomes, count regression, ordinal regression, or nominal regression. The same distinction happens when we get into multiple dimensions of sampling, where the vocabulary word that differentiates this scenario is mixed. So then we combine random effects that allow different sources of variance, one for each dimension of sampling at a minimum. So we can do a multi-level model, say, on a logistic outcome, and we'll do that tomorrow, in fact, for the predictor that happens to be binary. And by the way, the word linear does not necessarily mean that we're trapped into just estimating linear slopes. That word means the model follows a combination that operates as slope times variable plus slope times variable. The variable itself could be a predictor and its squared version, which would create the quadratic type of curves that we just saw in the keynote, but that's still technically a linear model. A nonlinear model would have like exponents in it or stuff like that. Okay, so levels of analysis, not just the stats, but the concepts behind the analysis. The whole goal in multi-level modeling is to be able to differentiate and quantify variability across each dimension of sampling separately. So in the context of clustered data, where we have people who are nested in clusters, we have between cluster variation, which would be considered level 2 of the model because people are nested in clusters, and that's inter-cluster differences, or the macro level. At level 1, it would be within clusters, so differences between people from the same family, from the same school, from the same group broadly construed. Those would be person characteristics in this type of sampling design. If you're not dealing with clustered data, the between and within parts still work. So in longitudinal data of occasions within persons, it's between person and within person. If you're dealing with, oh goodness, I don't even know. Let's go with multiple schools and multiple districts, then it's between district and within district. So even if your sampling design is different, hang on to the between as level 2 and within as level 1, and you'll be gold. The tricky part, though, is that variables that we think of as lower level within level variables are almost always both. So to the extent that I'm a person and I have my characteristics, I'm not randomly assigned to my family or my job or my school or anything. So there's probably some commonality there. And to the extent that people who belong to the same cluster have commonality, then what you're thinking of as a person variable is actually a cluster variable too. And each part of that variable, the person part and the cluster part, can have a different relationship with other variables. And being able to differentiate that is the tricky part of multi-level. So how we address that depends on what type of estimation we're using. If we're in univariate multi-level models like LME4, we have to do it in kind of a kludgy way. Do you know that word, kludgy? It means like less than ideal. Like if you picture like, you know, a hole in a pipe or something and you wrap it up with like tape to make it work, like that's kludgy. Or if you're like me and you get a rip in your clothing and you don't know how to sew and you put tape on that too, that's kludgy. And I would describe the way that we differentiate the between and within parts of a predictor in univariate multi-level models is kind of kludgy. The more optimal way to do it, if you have enough data, is to treat outcomes and predictors in the same way and let the model figure out how much of it is between and how much of it is within. So I want to show you a little bit about both of those things. We'll start with the kludgy way, and then we'll talk about the slightly better way because that's where the multi-level measurement models are going to end up. So, all these different dimensions of sampling, how does the model figure out how much we have of each kind? So one way to understand how these models differ from other things that you might know is a lens that I like to use in describing any model, and that it has two sides. And I talk about the model for the means as one side, And I can guarantee you that if you've only had, say, like a regression class or something, when you think of the model, this is what you're thinking about. I'm talking about the fixed effects, or what is known as the structural part of the model. And this is the part that we're used to caring about. So I have an outcome, and I have some predictors. How do they relate to my outcome? Does this predictor relate just by itself, additively? Does it interact with another predictor? Does it have a linear effect, or does it have kind of a bendy effect where it sort of levels off? All of those decisions about how a predictor relates to an outcome belong in the model for the means, and they're expressed as fixed effects. The other side, the side that you're not used to thinking about, and at some point earlier on, you may have been told to make assumptions about instead, is what I call the model for the variance. So the term here would be the residual part. It involves what is known as random effects instead of fixed effects. And the error part of the model would be another way to say this, or if you want to sound fancy, the stochastic part. Any others you can think of on that list? No, it's the leftover part. So this concerns how the residuals of the model, the leftover part of the outcome, are related across observations, and how they're supposed to be distributed across observations as well. And this is the primary way that multi-level models differ from traditional single-level analyses. So to be a little more concrete, I've got an example model here. I would consider this either a standard multiple linear regression if my predictor variables x1 and x2 were continuous or numeric variables. If these represented differences between categories, I might call this an ANOVA instead. But the key idea is that there's only one subscript here, P, for person, because that's the only way that the observations differ from each other, one dimension of sampling. So in this model, y is a variable that varies across people. Beta 0 is not. This is a constant. Beta 1, another constant. These are fixed effects, where fixed effects mean everybody gets the same. x1 and x2 are variables, and e is a variable. So the model for the means is this part, how the predictors relate to the outcome. And so each of these estimated constants, I call fixed effects, you might call intercepts and slopes. When I teach our introductory level course, I say fixed effects right out of the gate because I know there's another kind coming, and I want them to get used to that ahead of time. This E right here, that's our model for the variance. Now it doesn't look like much of a model, it's just one letter. But what we're saying is in this model, if we order up our linear regression, we are told certain things have to be true about E in order for our model results to be plausible. In standard linear regression, E is supposed to be, you can say it with me, normally distributed. What's another one? What's E supposed to be? Homoscedastic. It has homoscedasticity. And there's another big one. Starts with an I. Independent. So you are told these things have to be true. And you can make some pictures and do some more Rorschach tests to see if you can detect any heterogeneity. Well, what if it's not true? You take your ball and go home? No. So, yes, can we, please? Not yet. Soon. No, you fix it. It's like, well, I don't want that E. I want a different one. Yes?
What I also find kind of quite stunning if you're using Manifest approach, you're assuming implicitly that we have perfect reliability.
Oh, yeah. Yes. So I'm not even dealing with that yet. Mm-hmm. But yes, that is absolutely the case. Just as a side note, I was super uncomfortable last fall when I was teaching because I taught longitudinal models on Tuesday and Thursday afternoons as my first course. And we would talk about all this stuff with respect to an observed outcome, right? I was like breaking my own rules. Like, I'm just going to add some shit up. We're going to predict it as Y. It's going to be fine, right? There's no measurement error. Shh, don't talk about measurement error. And then at 2 o'clock, put on my SEM hat. You cannot add anything up. You need to fit measurement models. We need to look at reliability. We got to do all this stuff. And half the class were the same students. And so it was really weird for me to have to do that, but it's because you can't do everything at once. But you're absolutely right. We're assuming no measurement error of any kind, and we're not doing anything to address it if there is some, which there probably is in almost every case. So yes, that's another big one. So we got to fix it if any of these things aren't true. So if it's not normally distributed and constant variance heteroskedasticity is non-constant variance, is the way I prefer to say it. If it's not normal and it's not constant variance, then that's what generalized models are for, right? We switch to a Bernoulli distribution, or we switch to a Poisson, or a negative binomial, or a regular binomial, or something that fits better that has non-constant variance in it. The independent one, though, that's what we got to fix today. That's the big one. We have to allow e's from the same sampling unit to have whatever relationship that they're destined to have. Otherwise, bad things happen. So this is a type of model that's designed for a single level of sampling in which people differ from each other only in one way. So to make this a little bit more concrete, here's the simplest model that you would ever see in your life. This was the first thing that Jonathan tried to estimate in STAN. We call this the empty model. Empty means no predictors. So we have, for each person, one fixed intercept, and then E is how far off you are from that fixed intercept. Well, if you know nothing else about a person, what's your best guess for their outcome? The mean, right? That's what beta 0 is in the empty model. So if I wanted to make a guess for this person down here, that guess is pretty far off. So everybody gets a best guess of 90, and this person has a residual of minus 58. So the model for the mean is right there. And I think that's where the term comes from, because at the beginning of the process, there's only one mean. And after you add a predictor, then there's different means as a function of your value on the predictor. But if two people have the same predictor value, they have the same predicted outcome. The same conditional mean is what we might call that. And then this represents the model for the variance. So in this case, we're deviating each person's outcome from the outcome that's predicted, this y hat thing, which is just the mean. We're doing n-1 to account for the fact that we didn't know what the mean was. And this model, its job basically is to spit back the mean and the variance of the outcome as the starting point for how much variance there is to be explained. Now, most regression textbooks don't bother with this model. I do. For two reasons. Because it describes sort of like where total sums of squares comes from when I'm teaching regression, but it's also really important in multi-level models. This is our starting point. All the variance in the outcome is to be had. So what if we change the story, and rather than having one outcome per person, we have one outcome per person and cluster. So I've used different colors here to say that we have 3 different clusters, each that have 5 people or so. To the best of my PowerPoint drawing ability, okay? I'm not an artist. Not going to be. So in terms of starting off with our best naive guess, fixed intercept, grand mean, still a reasonable thing to do if we don't know anything else about a person. However, we do know something else. We know what cluster they came from. So rather than guessing the overall sample mean, why don't we refine that and guess based on their cluster mean instead? And that idea of starting from a different naive standpoint is the basis of what's going to be called a random intercept. In this context, forgive the Bayesian interlude here, because he's like, there's no fixed effects in Bayes, but we're in frequentist today, so it's okay. Fixed means everybody gets the same, and random means everybody gets their own. Fixed means it's a constant, and random means it's a variable. Those basic ideas transcend. So what we're doing then is taking what we used to just call all of this E variation, and we're dividing it up into 2 piles, as I would say, or 2 sources. We still have this grand overall sample mean here, but now we're allowing each cluster to have a different mean. So part of the variation in the outcome, we're saying, is level 2 between cluster differences due to each cluster having a different deviation from the overall sample mean. So I'm using U as the idea of how far off your cluster's mean is from the overall sample mean. And the variance of the U's across clusters, we're going to say, is tau squared by tradition. So this is between cluster difference. Why is it that some schools have higher math performance? I don't know, but I know based on the model to what extent that's true. And then within clusters, not everybody from the same cluster has the same outcome. Why is that? I don't know yet, but I can tell by how much that is true. So within clusters then, E swoops in to fill the gap that remains. E is the difference between where I am and the rest of my cluster is. So if I'm higher than my cluster, yay me, E is positive, and if I'm lower, then E is negative. And you put it back together again, though, you get the total variation. So we've just taken all of the unknown variability and split it into two sources. Why are some schools different from each other, and why are some people different from each other, even though they go to the same school? So notation with this, then. Introducing the multi-level way of writing models. So general linear model, empty model would look like this, where we have y for each person is predicted by a fixed intercept and the residual. It changes into this, where I have y for each person within each cluster, PC. Now I'm going to make a point about this because this is one of my pet peeves in life. Not everything has to be IJK. It doesn't. There is no IJK police that's come arrest you if you don't use those subscripts. I would highly, highly recommend, for the sake of working with your reader and their working memory limitations, to name your subscripts in a way that makes sense. So students in schools is a problem because I've got two S's. But I might do something like KS for kids in school or something like that. So you might have to get a little bit creative with your synonyms, but it is allowed to use different letters. So I for individual is sometimes used. I for item is sometimes used, right? You have I's in yours, that's right. So he took I, so I couldn't have that.
And he is person.
And
Kids are people too.
Yeah, kids are people. Yeah, just ask our kid. He's definitely a person. He's living his best life with his grandparents right now, having like ice cream.
High on narcissism.
Oh, yes. He is the best at everything. Just ask him. He is having ice cream for breakfast. Yes, it's highly normative. Just all of them are the best at everything at 8. Yes, indeed. So PC, person and cluster. So in my slides, I have a color coding scheme where things that are part of the model for the means are red and things that are part of the model for the variance are blue. And you'll note that beta 0 here is not in any color. That's not an accident. Beta 0 is not a thing. It is a placeholder. It is a backpack that holds the things that we actually estimate. So beta 0 C, because it's now a per cluster variable, gets defined at level 2. This is how each cluster gets its own mean. It starts off with this Y-looking thing here, that's gamma. That is the mean of the means. Yes, I knew I had words about this. And then U0 is how far off your cluster mean is from that sample mean. So clusters who are higher than average have a positive U, lower than average is negative U. So beta 0 is the backpack placeholder that holds these things. We swoop back down into the level 1 model, we pick up E as what's left. So E is then each person's residual from that cluster mean. And so you might be saying to yourself, is this convoluted multi-level structure really necessary? Nah, not really. Not for this type of model. At the end of the day, as one of our friends says frequently, we have 3 things in the model. We have a fixed intercept, we have a variance across clusters, and we have a variance across people within a cluster. And we're assuming right now that all the clusters have the same differences across their people, that it's homogeneous variance across clusters. You don't have to stay there, but that's where we start from. So this is what's known as an empty means, random intercept model, unconditional means model, or just empty model in multi-level land. And absolutely, this is where you start in multi-level analysis because it tells you how much variation is due to each source, and therefore, which type of predictor is going to be most useful. All right, I knew that was coming next. I made that joke earlier, but once I was giving a talk at another department, and one of the faculty members complimented me and said, "It was like you knew what was going to be on the next slide." Well, I made them, so that's kind of a low bar. But yeah, I knew that was coming. All right, questions? Am I talking too fast? No? Really? Okay. All right. I asked. So how much of each kind do we have? That's the first thing people might want to know. That's our friend intraclass correlation. So you've seen this probably in a bunch of different contexts in terms of ways of assessing reliability or concordance, but it is a ratio. Intraclass correlation is a ratio of how much variance is between clusters due to level 2 random intercept variance, or cluster mean differences, divided by the total, which is level 2 and level 1 put back together again. So level 2 cluster mean differences why don't all clusters have the same mean? And then E variance at level 1, why don't people from the same cluster have the same outcome? So we can think of this a couple different ways. One is it's the proportion of the total that's between clusters. That's the one that's a little more transparent. The other way that I think is more useful in cluster data in particular is that it's the average correlation of people from the same cluster. So ICC ranges from 0 to 1. If I had an ICC, say, of 0.1, which is, I think, fairly common in cluster data, that would mean kids from the same school have a correlation of about 0.1 with each other. In longitudinal data, this tends to be much, much higher. So in the examples that I give in class, we have interclass correlations up to 0.8. So the correlation of occasions from the same person might be 0.8. There's a whole lot of systematic level 2 mean differences at play. Another way to think about this is that it's an effect size for the extent of dependency in your data. So dependency is a word that sounds like it's a bad thing. Like, oh, I have dependent data, I have to fix it somehow. And for other people, dependency was the whole point of their study. Dependency means correlation. So this is an effect size for how much correlation there is, where the lowest that it can be is none, and the highest that it can be is all of it. So if I had an ICC of 1, what would that tell me? Go for it. Okay, you first and then him.
I'd say no within variation.
I would say that's correct. Want to add anything?
That's correct.
That's correct. Okay.
As I prove myself.
Yeah. So practically speaking, what that would mean is that every person from the group gave the exact same answer. Like they're all automatons who are exactly the same, and there's no variation within groups. If the ICC were exactly 0, what would that mean? See, it's 4 o'clock. I'm throwing softballs. Here you go.
No between variation.
No between. That means there are no cluster mean differences.
So, what I argue, if you have an ICC less than 5%, we don't need a multi-level.
Oh, I'm so glad you said that. That's like 2 slides from now.
Oh, okay.
Yes, yes. So at this stage, some folks might be tempted to talk about R-square or variance explained. And I would say absolutely not, and I will die on this hill. Have you heard that expression before? So die on this hill means like the expression pick your battles, right? You can't throw a fit about everything, you have to prioritize. Die on this hill means I have prioritized this battle and I'm going to throw a fit. Absolutely, to me, it does not make sense to talk about explained variance just because I've differentiated between cluster mean differences from within cluster differences. These are 2 different kinds of error. Why is it that some schools have a higher mean? I don't know. I just know that they do. Why is it that some kids did better on this test even though they went to the same school? I don't know. I know that they do. So it's identifying sources of variability that in turn can be predicted by characteristics at that level. So school things predict why some schools have higher means. People things predict why some people are better than their peers. So it's not explained yet. We're just divvying up the piles to see how much of each kind there is. Some folks get confused about ICC being the within cluster correlation because the numerator is between. So I just have a quick graphic about this. So here's my little picture that I had made. This picture would result in a relatively large intraclass correlation because the differences between clusters are large relative to the differences within. The opposite would look like this, where the clusters don't really differ as much from each other and the people are relatively spread out. So if I had this type of data, this would be a very small correlation because just knowing, say, that this person is from the green cluster, I wouldn't be able to do a very good job of predicting where the other green people fall. They could be all over the place. So this would be a relatively small intraclass correlation instead. So to your point then, is there something that you can ignore? The answer is going to be no. Here's one reason why that is. Clustering creates what's known as a design effect. It is basically a penalty factor for how much less information you have from your people than if they were from a non-clustered simple random sample. And the formula for a design effect has the level 1 sample size, so like the number of kids per school, times the interclass correlation plus 1. So that becomes the denominator that creates something called effective N. So ICC of 0 is the only situation in which this part goes away, and the design effect is 1, meaning there is no penalty. And this is a simple formula that assumes you have equal group sizes. The Snyders and Bosker textbook has extensions for that take into account heterogeneity of group size, which most of the case for cluster data there will be. So here's a couple examples. Let's say I have 5 patients from 100 doctors and a relatively strong interclass correlation of 0.3. That would create a design effect of 2.2. If I have 500 actual people, in terms of the information they provide me, I only have 227. What if I have a smaller interclass correlation, like only 0.05, and 20 students from 50 schools? That works out to be a design effect of about 2 as well, and it cuts my sample size in half. So where this comes into play is in doing power analyses. If you care about kids and you just happen to have to get multiple schools involved so that you get enough kids, you would want to be able to try and anticipate what your interclass correlation is and what your within school sample size is so that you can plan to have extra people to overcompensate for this clustering. So what about the case then where it is 0 and this goes away? Are you home free? The answer is no. The problem is that the estimation of how much of your variance is between versus within are tied together. Yes?
Sorry, maybe I didn't get this, but for the power calculation, how would you know in advance that this will occur? So is it something that you get from previous studies, or can you do some simulation with a smaller data set?
Great question. Question was, how do I figure out like what to expect for an interclass correlation? Well, you should probably, based on the sampling that you have access to, so the schools or the hospitals or whatnot, you would know what the average within group sample size would be. Interclass correlation is something that you could, in theory, get from other studies or pilot data. What you might consider is a range of plausible values. So for cluster data, you might try different scenarios going from like best case scenario of 0.01 to 0.1 or 0.15, something like that. For longitudinal data, I would go much higher. So like worst case or scenario, maybe 0.8 down to maybe 0.3. And then you could describe sort of my effective sample size I expect to be somewhere between, this number is best case and this number is worst case. And with that sample size, I have minimum detectable effect size of this to this. Like, I think giving ranges is a plausible thing. But yes, in theory, you should be able to find that from prior research. In practice, maybe not. So the estimation of these things means that let me say it this way. If I took this classroom and I randomly assigned all of you, say, into 4 groups, and I had each group compute the mean height of the people in those groups, do you think that all 4 groups would have the exact same mean height of their participants? Probably not. There's going to be a little bit of wiggle room, even though people are randomly assigned into those groups. So during the estimation process, they try to subtract off the amount of wiggle that's expected based on within-person variation. And it is literally the level 1 residual variance divided by the level 1 sample size as the estimate of wiggle. So they take that off, and then they come up with how much is actually between. Well, what can happen is that if you have a really good model in terms of person characteristics explaining within group person information, that wiggle gets smaller because the residual variance gets smaller. So less gets subtracted off, which means that your interclass correlation goes up after you include predictors. So it could start at 0.05 and be, it's fine, and it could end up at 0.2 by the end of your analysis, right?
Could I ask you practical questions? Or?
Certainly.
Yeah. For example, if I have longitudinal data and I expect an ICC of 0.9 or so, so worst case, do I need to collect any level 1 predictors because I can't explain differences anyway within persons?
So the question was, if I'm expecting a huge ICC in a longitudinal context, say 0.9, should I bother collecting within person time varying information? I would still say yes, because to the extent that people are consistent, that's person information. So if you ask me every day of the week, how stressed are you today? Some days are worse than others. Like yesterday, I was not teaching, not as stressed. Today, a little more stressed. But then there's going to be differences. Some people say they're stressed all the time, and some people say that they're not as stressed. So what you're thinking of as time varying is actually a person thing in disguise. And so to the extent that the person part of that can explain part of your between person, it's still a good idea. Yeah, there's no like, you can't absolutely do this until you hit maybe 0 or 1. Anything in between, I think you have at least a reasonable basis to try to collect variables at each level. So yes, your interclass correlation can go up if your level 1 model explains a lot of person variation. So I would say, yeah, just plan to do the multi-level model. Only if the interclass correlation is 0 and stays that way no matter what you do, could you make an argument that it would be reasonable to ignore it. There are ways of adjusting for cluster differences. So there's something called cluster corrected standard errors. Stata as a software package has a lot of routines for this, and Plus has this. I'm assuming R has stuff for this because R has everything. That is an okay thing to do in certain situations, but what it will not solve is this idea that every person variable that you're measuring is also measuring their cluster at the same time. And so that is the part that makes this tricky, is being able to differentiate the effects of predictors on level-specific outcomes. So there are really two differences in how you can model cluster differences. You could treat them as fixed effects. So there are certain disciplines, I want to say econometrics might be one of them. There have been, I'm trying to remember the people that I've talked to at the university. I get students from all over campus, and there are certain students who ask me about this. For instance, there's something called a Hausman test, where you're supposed to be able to evaluate whether fixed or random effects should be better. And if you don't have that many clusters, including them as fixed effects might be a reasonable thing. So if you only have 10 schools, put in school ID as a categorical predictor and call it good. You don't need a multi-level model then. You've saturated the model with respect to all the reasons why clusters differ from each other by putting in cluster ID. That's fine. So this is useful as a strategy if you don't have that many clusters, or if you care about specific cluster inferences. So let's say that you're doing a cross-country study where you might have 30 different countries. And if you're specifically interested in saying, this is the predicted outcome for people from Germany, and this is the predicted outcome from people from Sweden, and this is for Switzerland, and you want to talk about the specific instances, fixed effects is the way to go. What we're going to do, and what tends to be more useful, is a random effects strategy. And that means you turn cluster into a level by estimating at a minimum between cluster differences as random intercept variance. Then you can predict why is it that some countries have higher outcomes than others, why some schools have students who do better than others, with school or cluster level information. You can't do that with fixed effects because it's redundant. All right, so in terms of adding predictors, let's see, it's already 4:13, probably stop around 4:30-ish. Would that make sense? Or 4:15?
Well,
Yeah.
the schedule today is till 5:45.
I know, but we wanted to give them time to like talk and
Whatever.
all that stuff.
You're the boss.
I'm the boss. What do you think, folks? When would you like to be done today? Because that dictates sort of how far into the cycle to go.
I have the feeling that the questions come when the combination of the methods come.
Yes.
So I would like to have more time when we need to combine the methods.
Yes.
And
Okay.
maybe now it's okay to have a bit like a faster pace, but then when the combination happens and this is like the new thing, then there will be lots of questions because then it comes to, okay, how do I apply?
Okay. That seems reasonable. So maybe go like closer to the end today, but not to the very end because I'm not a sadist. And 5:15 is like a lot for being talked at all day long, right? Plus, some of us are going to network tonight too, right? So I got to save something in the tank for that. All right, so we'll talk about level 2 predictors because this is the easier one. So adding in cluster predictors is absolutely not different than in standard regression type things. Everything you learned about that readily applies. So in terms of notation, for instance, if I have level 1 students and level 2 schools, I'm going to stick with PC for my subscripts here. At level 1, the model would still look like this. What we would call an unconditional level 2 model, meaning I don't have any predictors yet. This is the empty model from before, would look like this. If I added some predictors, so I have level 2 x1 and level 2 x2 as sort of generic representations, note that they both get a C because they vary only across clusters, not people. So I used to be somebody who hated subscripts and thought they were unnecessary. Studying these models changed my mind. Subscripts are everything because they tell you what it varies over if it varies. So anything in your level 1 model that's a variable here, y and e, it needs a PC. Anything in your level 2 model only needs a C. In terms of the subscripts here, the first subscript keeps track of which beta in level 1 you're predicting. Right now, I only have an intercept, so that's why all 3 of these red gamma terms start with a 0. The second subscript indexes which predictor of that beta you're on, where we start counting at 0. So level 2 x1 is the first predictor of beta 0. This is the second predictor. Can you guess what it would be if I had another one? Softball. 0.3. Yes, exactly. So gamma 00 here is my fixed intercept, and it means the exact same thing as you were taught an intercept means way back in the day. It's the expected outcome when all your predictors are 0. So what that means depends on the scale of these 2 predictors. So what's different then in terms of the random intercept is its interpretation. Before we add any predictors, this UOC represents the idea that each cluster has a deviation from the grand mean, and the variance across clusters, this is all the variation there is to be had. This U is variation, represents the idea of variation left over. So this is the remaining deviation after adjusting the cluster's prediction for their standing on these 2 things. So this is U variance left over. For this reason, some textbooks will call that U, where my mouse cursor is here, a level 2 residual, where residual means leftover after. I don't say that because I think it's confusing. I reserve the term residual for the E. So right now, all the E variance is still there. We have not done anything to explain why some students might have a higher outcome than other students. All we've done is explain why some clusters have a higher mean outcome than other clusters. In terms of effect size, you can convert your t-test statistic of estimate divided by standard error into a D or a partial R. Those formulas that you can use on single level models also work fine on multi-level stuff. You can also talk about R square, but you need to do so carefully because there are approximately 37,000 kinds of R squares that have been invented for multi-level models. The one that I tend to use, actually there's 2, this is the first one, is something called pseudo R square, and that is not me being funny, that's literally what it's called. The idea of pseudo R square is that it's a per variance component measure. Like of the level 1 E variance, how much did you get? Of the level 2 random intercept variance, how much did you get? Like of each. So it's a very specific measure of variance explained of that kind. How much of the cluster mean differences are related to these predictors at level 2? How much of the within cluster person-to-person differences are related to these predictors at level 1? That's one thing that I like to do. The downside of this is that it can go negative, particularly for effects that are not contributing to the model. Variance components, the more you have, the more they sort of slip around each other. And there are different ways of computing this that don't rely on the idea of a baseline model, that instead rely on model implied variance. Here's a couple references for those. There are R packages that go with them, of course. And the other one that I like, which is complementary, is total R square. And this relies on the same definition of R square as what you have in linear regression. So it can be useful for people who are less familiar with multi-level models to understand. It can also be useful in models where you have a whole bunch of different kinds of random effects. So every software package on the planet has the capability of generating a column in your data set of predicted outcomes from your fixed effects. Like, what is y hat for every case, right? If you take that y hat column, you can correlate it with the real y, that's r. You square that r, and that's r square. So total r square puts all the different kinds and piles of variance back together again and just says, how much of math did I explain, right? Not between and within math, none of that, just math, period. So I think this is useful to sort of get an overall picture of how effective your model is. A more drilled down picture of each part of your model can be given by pseudo r square. So whenever you report these things, I would definitely describe it in words, give a formula, and give a reference so that people know which of the 37,000 kinds you are using. And maybe a reviewer or two wants you to use a different one, but at least they understand which one you chose. Otherwise, if you just say r square, it's ambiguous as to what it means. All right, so part one then we've gotten through. The idea of these models start with no predictors. We first need to figure out how much sampling variance, let me say that again, how much outcome variance there is due to each dimension of sampling. That's step one. That's going to tell us which types of predictors are going to be most useful. We can quantify how much variability we have at an upper level with an intraclass correlation. And higher intraclass correlations combined with higher numbers of people per cluster create stronger design effects, which means we really have to pay attention to this. It results in a smaller effective sample size. And we can use the regular types of things to put in level 2 predictors. So we can use walled tests or modified versions that have denominator degrees of freedom for significance if we want to in a frequentist context. We can compute effect size in usual ways. We can talk about how much of the random intercept variance our cluster predictors have explained. And we can talk about how much total variance they've explained as well if we want to. All right, there. Sip my apple juice. Questions? For now, anyway. Yes, please.
Can you say why there are so many pathways?
Why are there so many? Because people have tried to quantify different levels. So, like, there were earlier, the earliest versions, I think, were in Radenbush and Breich's textbook and Snyder's and Bosker's textbooks. They have a level 1 r square and a level 2 r square. That's fine for this type of model, which is relatively straightforward, where there's only one kind of variance per level. But what we don't have yet is something called a random slope. And that's the idea that the effect of a person-level variable on a person-level outcome differs by clusters too. That's where we're headed next. And so those level-specific formulas didn't have a way to put that into the picture. There are then different ways of either incorporating those types of between cluster slope differences into explained variance or not, which are known as either marginal or conditional r squares. And then there's pseudo r square for each pile that you can have, as well as each variance component. So it's different ways of like carving up the total variation or lumping it back together. And I think the core thing to think about is that each predictor that you put in the model has a job to do. Like, it is going to reduce one or more of them. And understanding which one that is based on the composition of the predictor then logically dictates like what kind of r square would make sense for it. So if you follow that logic, which I've only gotten just this much of, then I think it will become more straightforward which ones that you would want to do. I think, like, in practice, I would recommend just these two, sort of, because pseudo r square is per variance component, and total r square is more of a, like, put it all back together again, global effect size. You can kind of think of these as like global fit and local fit, kind of, like it's like sections of your model versus putting the whole thing back together again. Does that help? Yeah, I tried, at least. I tried. All right. Other questions or comments? No. Okay. Then, here's the hard part. Level 1 predictors. If you learn nothing else from me, ever, learn this. Don't do this. It looks like it should be fine. So if I have a level 1 predictor, that's a person thing. So previously we had some level 2 predictors. I have level 2x here, just one of them. Well, what if I just put my level 1 person predictor in, right? So that's a person characteristic in this context. I can put it in the level 1 model to predict this E variation, why some people in my cluster do better than other people in my cluster. It's because of this characteristic, right? Fine. No. So for the same reasons that we needed a multi-level model to figure out how much variability in the outcome is between versus within, we can't do this because we need to figure out how much of this level 1 person predictor is between versus within. It is literally the same problem on the predictor side. So it looks like this should be fine just to say, well, this is the effect of the person predictor. But the fact that it has these 2 subscripts is your first clue. It's not a person thing. Most likely it is a cluster thing too. So this problem, I think, it certainly exists in clustered data. It is exacerbated in longitudinal data because the ICCs, the extent of person constancy tends to be much higher than the extent of cluster constancy in these things. So here's the classic example of where this would go awry. So each level 1 predictor across sampling designs is almost always 2 predictors and 1 at a minimum. So textbook example, something like student socioeconomic status. This is what's used in the aforementioned textbooks, Radenbush and Bright, Snyders and Bosker. It may be true that some kids come from families that have more resources than other children. So you can think of that legitimately as a student or person level characteristic. But at least where I'm from, children are not randomly assigned to schools. You go to the school that is closest to where you live, and where you live has a commonality in terms of how much resources it took to buy into that neighborhood. So to the extent that children who go to the same school come from similar backgrounds in terms of their socioeconomic status, then what you're measuring as a student characteristic is actually a school characteristic too. And there may be better ways to measure that directly at the school level, but at a minimum, indirectly, most student level variables will be school level variables. In longitudinal data, questions that people answer repeatedly over time are also likely to have some constant person information. So just like in the talk we just saw, some people have higher narcissism all the time than other people, and within persons, your narcissism may change over time. So it's not just narcissism at this occasion, it's you have to know who it came from because that's the part of the story. So differences between students from the same cluster can explain outcome differences between students, but then between cluster differences in the predictor can explain random intercept differences at the same time. And how do you know if this is going to be a problem? Same way that we know how much variation there is at each level in an outcome. Fit an empty model for the predictor as an outcome and compute an inter-class correlation. So we're going to do that in the example. We have a very simple variable, which is whether or not a student in our rectangular Midwestern state receives free or reduced lunch. It's a binary variable. So I have to change the model to account for the fact that it's binary. I need a logistic version, but beyond that, the same principles apply. So if I have an inter-class correlation that is less than 1 for my person level predictor, that means that it has at least some person level within cluster information, and therefore it could be in my level 1 model as a predictor. If my inter-class correlation is greater than 0 for my predictor, then it's not just a person thing, it's a cluster thing too. And the cluster part of it needs to go into my level 2 model to explain why some clusters differ from each other. It operates on both levels at the same time, potentially, if it has variance at both levels at the same time. So only if it were like 1 or 0 would you be free of having to worry about this. If it were 1, if a predictor had an inter-class correlation of 1, then that would mean it's only a cluster thing. It's a level 2 predictor. So that's another way to think about it. Cluster level predictors have an ICC of 1. It is the same for everybody from that cluster. In clustered data, it's hard for me to think of a variable that would have an ICC of 0, meaning it's just a within cluster variable. But that could happen in longitudinal data if you have balanced time, and you think about time as the predictor. If you have everybody coming at time 1, time 2, time 3, time 4, there's no differences between people in when they came. There's no between person differences in when time was. Then that's an interclass correlation of 0, meaning time can't be in the level 2 model because it doesn't have level 2 variance. So the ICC for a predictor is a limiting condition. It says, does it have variability at that level? If so, it needs to go in the model at that level and potentially have a relationship to the outcome at that corresponding level. How to do that is the tricky part. Yes?
Doesn't school mean a estimated quantity? You're using it as a predictor, like it's known with perfect reliability?
All of this is perfectly reliable.
Does school mean? I mean, does it not have variation? Standard error of the mean?
Well,
Okay, I just thought I'd ask.
no, but where you're headed then is the ways to put it in a level 2 model. Some of those address the fact that it is an estimated quantity, and some of those don't. So how to do it is the tricky part, but this is the fundamental idea. Anything that you think is a level 1 variable is probably not just level 1. It's level 2 and higher as well. Okay, how are we doing? Yes? Only one thumb this time. No, there's 2. I have a thumb system that I do when I'm teaching. I developed during the pandemic when people were sometimes on camera and sometimes not. I've got thumbs up, thumbs sideways, which is like so-so, and then thumbs down. Zoom recently introduced a thumbs down button, by the way. So I used to ask them for other, like, can you just give me like the poop emoji or something if it's thumbs down, and they would do that instead.
I used to do that.
Yeah. Yeah, you can use emojis in clever ways, but since we're in front of each other, we can do up, sideways, or down. It's like a little thumb thermometer. All right. So in terms of the relationships between predictors and outcomes, the between part of the predictor and the within part of the predictor could have relationships that go in the same direction. So if we think about socioeconomic status, resources broadly construed, children from backgrounds that have more resources probably have higher achievement for whatever reason, right? So we can think about that as within a cluster, children who have more money in their families than children from the same school who have less money may have higher achievement within the same school. Between schools, schools that have more resources, meaning rich kids go there, right? That's an estimated quantity, but that's the idea. Schools that have more money than other schools may have higher average outcomes than other schools. So in that case, SES is good for you at both levels. But that's not necessarily true for all types of variables. There's an example that I like, so I stole it. This is from Curran and Bauer's chapter. No, it's not a chapter. It is an annual review of psychology. I put the link there. And the story was that Patrick was listening to NPR one day, National Public Radio, and they had a story about this, and he took it and put it in the chapter. So the relationship between body mass and life expectancy in animals. Within a species, relatively bigger animals have shorter life expectancy than relatively smaller animals. So overweight ducks die sooner than skinny ducks. But across species, bigger animals live longer. So whales live longer than cows, and cows live longer than ducks. So what is the relationship between body mass and life expectancy? There's no one answer. It's like, well, what are you talking about? Are you talking about being a big duck? Are you talking about being a big whale? It's not the same thing. In humans, an example that I like is exercise and blood pressure. So your blood pressure is often measured when you get your annual physical as a proxy for some sort of overall health, right? And people who tend to exercise and eat their vegetables and take care of themselves may have lower blood pressure than people who don't engage in as many of those health behaviors. But when you're actually moving, relative to when you're sitting still, your blood pressure is higher, not lower. So the relationship is different whether you're talking about between persons relative to other people. Healthier people have lower blood pressure. Within persons, when I'm moving, it's actually higher. Both of those are true at the same time because they mean conceptually different things. So overall blood pressure is a proxy for overall health. Current blood pressure is a proxy for something else. And so beyond just these sort of conceptual reasons, it's still the case in longitudinal data as well. Like the reasons why some days are harder than others are entirely different reasons than why some people have harder lives than others, right? Those are completely different things. But beyond that, math. These are unstandardized slopes. So a slope is the change in y for a 1 unit change in x, right? If we're talking about level-specific x and level-specific y, the only chance in which these slopes are going to be the same number is if both variables have the same ICC and they're both on the same scale. Otherwise, the math doesn't work. What a unit is differs across level 2 and level 1 and x and y. So for those reasons, most of the time, these within slopes and between slopes are not going to be the same number. That means we need to make sure that they're separated somehow in our models. All right, so what not to do, the one thing I hope that you take away from this, is a problem that I call a smushed effect. That's my term. I made it up. After years of teaching these models, I started to make this gesture. They're smushed together. And so that became my thing. And so in my book, I did write a textbook. It was published in 2015. It took me 5 years of my life to do it. I signed a contract in 2018 for a second edition that I haven't started yet. It's been due a few times, but I just keep, pushing that down the road. In the index, I made sure there was an entry for smushed effect. That's mine. I would also accept smushed with 2 O's as an alternative spelling, smooshed effect. If you don't want to say smushed effect and you'd like to sound a little more professional, I don't blame you. You can call this a conflated effect, a convergence effect, or a composite effect. There's a lot of synonyms. But the key idea here is that in this model, I have a slope that is allocated to my level 1 person predictor. So beta 1 here, because it's the first predictor in my level 1 model. C, because potentially each cluster could have their own. That gets defined by its own level 2 equation with only this fixed slope in it, just a fixed effect. That means this model is assuming that every cluster has the same slope for this person level variable. More problematic, though, is that this one slope has to do the job of the level 2 part and the level 1 part simultaneously. That means it's constraining those two between slopes and within slope to be equal to each other. That's why it's wrong. It's not going to be a perfect mixture of the two. It's going to be weighted. Most of the time, it will look far closer to the level 1 slope because that's where all the information is. You have way more people than you have clusters in most of these designs. So it's weighted closer to the level 1 slope. That means it's the level 2 model that is screwed up by the omission. And I will say that this is not unique to psychology or multi-level models. This is related to what's known as the endogeneity problem in other fields that are worried about this. And it turns out that if you do something like a Hausman test to say whether you should have fixed versus random effects to control for cluster dependency, and it comes back as random instead of fixed, you have this problem. What that means is that in your data, you have detected a correlation between a level 1 predictor and a level 2 U. The only way that can happen is the level 2 part of the level 1 predictor is correlated with the level 2 U. Variables don't cross levels. It's the embedded cluster information in your person predictor that is the problem, and it has to be distinguished. So there's a couple papers I can refer you to if you're interested in more about this, but point being, different fields have been worried about this under different labels. It's the same problem. So this is solved, by the way, if you represent clusters using fixed effects instead, because knowing in your model whether it's cluster 1 or cluster 2 or cluster 3, you've controlled for all the cluster level differences. That means what's left for your person level predictor to do with its slope is just the within cluster part. So then the problem is solved via statistical parceling and not manual parceling. I can never say that word correctly. So there's 3 strategies basically to fix this problem. Here's what it looks like graphically. So note I'm using color here deliberately again. I've got my Y per person per cluster here. And the first thing we do with our Y observed outcome, note it's a box, because this is not a measurement model, this is just an observed variable. Don't tell me it's unreliable, I don't want to know, that's tomorrow. The first thing we're going to do is split it up into what is level 2, between cluster Siri says she doesn't have an answer for that. You know what, Siri? I don't either. That's why this stuff is hard. Y is going to be split up by the model, and note that these are circles, that is not a coincidence. A random effect is a latent variable, by the way. That is the same damn thing. They are isomorphic, so some would say. I had students ask me, what does isomorphic mean? It means same damn thing. Because people only use that word when they're indignant about the fact that it's the same. So level 2 between cluster random intercept variance, the extent to which is found by the model as a parameter, and then how much of the within cluster level 1 residual variance remains. So what was sort of green and purple has been distinguished into levels. Well, over here, I've got my level 1x that's also a blend of 2 things, but I haven't separated it. So if I give it a slope predicting y, another way of saying that is that I'm saying the extent to which the green part of my predictor predicts the intercept is the same to which the purple part predicts my level 1 residual. That's what I'm saying. So I got to find a way to allow these 2 paths to have different estimates in order to solve this problem. So 3 different kinds of effects then that you might be interested in for any level 1 predictor. The first is the obvious one, what I would call the within cluster effect. So if I have a higher predictor value than other people in my cluster, relatively speaking, do I have a higher outcome value as well, relative to other people in my cluster? If so, that should explain the outcome's residual variance to some extent, and that would be the relevant pseudo R-square. So if I go back to the equation here, here's the trick. The predictor explains whatever variance is in its row here. If I put in my level 1 predictor, it explains E. If I were to put in something in this row, it explains this U. So equations can help you figure this out. So level 1 within part of the variable explains level 1 residual of the outcome. Level 2 between, so the clusterness of your person predictor, when represented directly as a new cluster predictor, can then explain level 2 random intercept variance. So this would usually be the average value across people from your cluster. So the average SES of students from the same school can predict why some schools have higher means than other schools. The third one is a bit of a headache. It is what's known as a level 2 contextual slope, and it is not a synonym for level 2 between. These are 2 different things, but they're both at level 2. Any one model will give you one or the other, and part of the difficulty with these is figuring out which one you got. Level 2 contextual can be understood 2 different ways. The first way is my preference because it's easier. It is literally the test of the difference between the within slope and the between slope. How different are they is the contextual slope. It is between minus within. The way that tends to be more useful for people who prefer to set up their models this way is it represents the incremental extra effect of being from a cluster that has a high mean on this person variable. So in the context of SES, if I'm a rich kid, yay me, right? My achievement's higher than other children. If I go to a rich school, do I still get an advantage? And everyone in my rich school gets an advantage after I control for how rich I am. So what is the incremental contextual effect of the cluster after controlling for the person's information? That's what a contextual effect is. And in cluster data, that tends to be of interest because they want to be able to say, after controlling for person characteristics, the environment you're from matters extra. The level 2 between is not controlling for the person level 1 information. So each variable then can tell you at a minimum these 3 different things if it has variability at each level. So here's 3 different strategies, just an overview to talk about what the choices are, and then I'll go into each one in a little bit more detail of how to make sure that you're not smushing your level 1 within and level 2 between effects together in your model. The first strategy is my personal favorite because you can't screw it up. This is like dummy proof. You do the work ahead of time. This is one of the kludgier ways, but it always works no matter how small your sample is. And it's easy to do, and you can do it in almost any software package like LME4, any of the mixed packages in SAS, Data, SPSS, etc. You carve the variable up yourself. It's called cluster mean centering, or what I call variable centering. You take out the cluster part. You subtract off the cluster mean from the variable to begin with. You take what's left that only has within cluster variation, you put that in your level 1 model. You take the cluster mean you subtracted off, you put that in your level 2 model. Then each predictor only has the variance at each level, and it can only have that effect. So if you do it this way, you are guaranteed to get within slopes and between slopes, the end. Question? Give me about 2 minutes and I will get there. Because it's not the centering that I think you're thinking of. Centering would be like, I subtracted 3, right? Like that's centering. That's constant centering. I'm talking about variable centering, where I subtract a different number for each cluster. So I'm isolating the cluster variance off of it that way. That's why it's not the typical centering that you would do to change what your intercept means or change what your main effects mean as part of an interaction term. That's constant centering, where everybody has the same centering value in the code. So, but I will get there, I promise. Okay. Grand mean centering. You don't carve it up on the front end, and you have to make sure that you've got everything in the model that you need. This is more prone to being screwed up. If you do it this way, as long as you put in the cluster mean, still, you end up with within slopes and contextual slopes. These are both available because you're treating these as observed variables. You're assuming they're perfectly reliable. The kludgy ways. Option 3 is to go multivariate. So this is what's known as latent centering. And I can foreshadow this. I have a picture coming, but I'll show it right here. Just take my X and make 2 circles out of it too. Doesn't that make sense? I did Y. I let the model figure out how much was between and within. Can I just do that for X at the same time? Sure I can. It requires multivariate estimation to be able to do that within SEM, multi-level SEM, and multi-level measurement models. Where we're eventually headed is between and within theta. Oh, now I get why she's talking about this. That's where we're headed. This is between within on a sum score, but we can between within our thetas as well. So that's known as latent centering by the M+ folks and a few other folks, and this is probably the optimal way to do it because you're letting the model do the carving up. You're not treating it as a perfectly observed variable like the school mean. We're going to show you how to do this. The catch, though, is trying to figure out what you get at level 2, whether it's between or contextual. That's the hard part, and I wrote a whole article about it because I got really confused and I thought I need to write this down so other people are not as confused as me. Did you have a question? No? Okay.
Yeah,
kind of a question?
You're not adding here the cluster mean as a level 2 variable.
Yes, we are. We're doing it as an observed variable in options 1 and 2, and we're doing it as a latent variable in option 3.
Okay, so you have the level 1 predictor and the group mean, both entered in the model.
Yes. Yes. So in each of these 3 approaches, there is something at both levels. The question is what that something is. So I'll show you each of the 3 then, and then we will demonstrate those tomorrow, keeping an eye on the time here. All right, so cluster mean centering. This is where you carve it up yourself so that you know what you have. So step 1 would be compute the mean across people from the same cluster of your level 1 predictor. So you would do this literally aggregate across rows, make a new variable, merge it back into your data set, Jonathan wrote a function in R called add unit means that I'm going to borrow to do this. He's much better in R than me. So this variable, just like any other predictor, now it's the cluster mean of the student information, person information. You would center it at a constant so that 0 means something, so that you maintain an interpretable intercept. Doesn't matter what the constant is. You can leave that off if you want, but it's helpful to keep the rest of the model in check. So if I picked the sample mean of this variable as my centering constant C2, then what it would mean to be higher on cluster mean X, a positive number would mean I'm from a cluster that's higher than other clusters, and negative would mean I'm from a cluster that's lower. So that goes in the level 2 model, cluster mean X, where X is my person variable. Then within, so I'm creating a new variable ahead of time. I'm naming it within cluster X. It varies over persons and clusters. And I take my original person variable and I subtract off the level 2 mean. So this is not a number. This is a variable. That's the distinction. So I have taken away all of the information about which cluster I am from, and I've left only relative information about where I stand relative to my cluster. So if I have a 0, that means I'm on average relative to my peers. If I'm positive, that means I'm higher than my peers. And it's kind of weird to think about, well then, like, if I have a 1 and someone else has a 1, like it's not really the same 1 because it's 1 more than your cluster. It's not weird anymore if you make sure you get the green part in the model. The level 2 mean goes in. So the reason I like this is that cluster mean X here only has cluster information in it because it's the mean across people. You've removed all the people information. Within cluster X at level 1 has all the level 2 information removed, and it's only within. So you're separating these ahead of time so that you know exactly what they mean. So it would go like this in a model where I have within cluster X as my new level 1 predictor. It only contains relative information about where I stand. So the slope that it gets, gamma 1, O, right here, this is the effect of having 1 unit more X than anyone else in my cluster. 1 unit richer than other kids who go to my school. The slope for cluster mean X, then, is the effect of having more X than other clusters on average. So a 1 unit more money on average than other clusters, than other schools. That's my slope. And because each of these variables are uncorrelated, they don't have any collinearity, they don't compete. So that means that regardless of whether you have one or both in the model, purple is within, green is between, the end. And that's why I say I like this, because you can't screw it up. You do the hard work ahead of time. So it would look like this. I have taken what was a person and cluster information variable, the purple and green there, and I've split it into observed variables. Level 2 is cluster mean, which is directly analogous to what the intercept represents for y. The random intercept represents cluster mean differences. This box represents cluster mean differences. Then within, my original person variable minus the cluster mean only has level 1 variation. That is directly analogous to what happens in the model in forming residual variance. So this is the brute force version of what the model is doing when it splits out your variance into level 2 and level 1. So this is the basis of the multivariate approach, is rather than do it with boxes manually into observed variables, let's let the model do it into latent variables instead, the same as what happens on the left-hand side. Okay. Does that help? Or am I making it worse?
Can you try to put it from classes to people and days? I'm struggling.
Sure.
It's easy to understand everything once, but I'm not sure if I really understand the between level of clustering. So it would be the mean across people, but no, it's a variable, it's not just the mean.
No, it is. So this box right here is like if I take all the rows of people from the same school and I take the mean across those people and I save it as a new variable and merge it back in. And then the next school, the mean across all those rows, merge it back in. Next one. So it becomes a level 2 school characteristic. So maybe if I be a little more concrete, the example that we have, the person predictor, is whether a child gets free lunch. It's a proxy for socioeconomic status that's commonly used for better or worse. In our data set, there are some schools where none of the kids get free lunch, and there are some schools where most of them do. Those are different contexts. So if I compute the proportion of children from the school who get free lunch, that is now a school characteristic. Just like whether it's public or private, whether it's urban or rural, or anything else that's true about the school as a whole. And so schools that have more poor kids have different outcomes than schools that have fewer poor kids. That's the clustered example. So then this slope right here would be the effect of going to a school that has a lot of poor kids or not on the school's mean math achievement. The level 1 within would be the effect of being a poor kid or not within a school. Two kids who go to the same school, same context. One gets free lunch, one doesn't. What's the difference on average in their performance? That average gap is right here. That's the within slope. If you want a longitudinal example, so give me some variables. Can you make something up? Stress and grumpiness, maybe? Negative affect, as they call it. Yeah, I used to be a psychologist, remember? Yeah. I actually had a paper about stress and grumpiness and glucose and grumpiness, and we called it grumpiness for that reason. So people who are more stressed out than other people might be grumpier than other people. That's level 2 between. On days where I am more stressed than usual, I am grumpier than I usually am. That's within. Than usual is the key, because that means I've subtracted off whatever usual is for me. Okay, I think this is probably a good stopping point. So cluster mean centering is what we've talked about as a strategy for separating level 1 effects. What you get, because you've isolated the sources of variance in each variable ahead of time to be level specific, you get the level specific relationships. There's no worry about smushing or conflating effects because you've separated them a priori. That's my preferred strategy. Okay, yeah, 4:57. I think we're closing in on the end of our attention span. I can feel it. Don't feel bad. I'm right there with you. That's all right. Let's questions. Let's talk questions. Or can I make any other connections or examples? This is like free stats consulting. Tell me your variables. I'll give you a story. Yes.
For instance, in the stress example, if we have different age groups, children and adults, older adults, would you do the same cluster, the same procedure, or
Is this
would you
is
consider
a long?
the age groups as clusters?
Oh, okay. You want to go that? So people within like age cohorts or age groups or something?
If there is no continuous age.
Not a continuous age. Okay. So then, stress and grumpiness. So if
Say 5 days.
in 5 days, or
Sampled on 5 different days.
oh, okay. So do you want a 3-level example, or do you just want age to be like a level 2 predictor, a person characteristic in that case?
The age is not a continuous variable. So
It can still be a predictor. Absolutely.
yeah.
Okay, so sample people for 5 days. We're measuring their stress and their grumpiness, and the people are of different ages. Okay, cool. So then everything that I said for her example still holds. So the extent to which people who are more stressed out than other people are grumpier on average than other people. Like you could find that with a cross-sectional study, right? You don't need the 5 days. You just ask them once, how stressed are you? And then you'd have this green part. If you go to the trouble to sample them for 5 days, you add the purple part, then on days where you say you're more stressed than usual, relative to whatever your own average is? Are you more grumpy than usual relative to what your own average is? The relative to your own average is on the x side, your person mean in that example, and on the y side, the random intercept. That conveys what usual is as mean differences. Now, if you want to put age in as a moderator, the link between average stress and average grumpy increases with age, decreases with age. The extent to which being more stressed than usual translates into more grumpy is worse in young children. I can verify that. Anecdote. So yeah, each of these slopes is just one relationship that could be moderated or mediated or whatever you have in terms of your constellation of hypotheses and variables. My key point is that they're two different things. Even though you're thinking about like stress on a daily basis, it's not just daily stress, it's people stress too. And children free lunch is not just a child characteristic, it becomes a school characteristic as well. Same idea. Okay. Others? Jonathan, do you want to do anything? You want to add anything?
No.
How's the WAIC going?
Oh, it's fixed.
It's been fixed.
Model 8 with the regrounding issue.
Oh.
So.
Did we fix it? Yeah, the grand finale model 8 for this whole week would not converge. So he's been troubleshooting this for like a week, 2 weeks, a month. Okay. So yeah. So he's multitasking. No problem with that.
And we will update the
Yeah.
material so that it's all up to date. We'll also add in the links to the videos as well as we go forward. That's just
Yes.
forthcoming. I'm sorry, it's taking a little bit extra time to get those to you.
Yeah, the videos will be on YouTube. So you will be able to view them at your leisure. And part of the reason we do YouTube is because they do captions. So they do a pretty good job of captioning this. By the way, the captions are searchable. So if you want to say, where did she talk about smushed effects again? You can type in smushed effects and it will go to that part of the video. My students really like that because I tend to wake them up by doing this, homework question, or something like that, and then they just search for that term. So.
Frightening.
I know, but sometimes you got to, right? I teach back-to-back on Tuesday, Thursday afternoons, and several students take both classes. So by, like the end of hour 2, sometimes you just got to like that. But not you. You're all attentive.
There's coffee.
There's coffee, yeah. My classes aren't catered, so maybe that's my mistake. I might have better luck if I keep caffeinating them throughout the afternoon. All right, I think 5 o'clock is good enough for today. What do you think? Okay, all right. We will hang out as usual, and then I hope to see some of you later this evening. Otherwise, enjoy your night, and we'll see you tomorrow. Oh.